In this video, we're going to talk about section 4.3 for Calculus 1, which talks about extrema. When we talk about extrema is a word that includes both maximums and minimums. Maxima would be plural, maximum is singular, and the same for minima and minimum. If we want to refer to the extremes on a graph, a maximum and a minimum, then we call them extrema for plural and extremum for singular. So in this section, that's what we're going to be dealing with. Now, when we talk about an absolute maximum, we're not talking about the absolute value. What we're talking about is the highest possible y value anywhere on that graph. So if you think about the Earth, we do have an absolute maximum on Earth, which is basically Mount Everest. The height of Mount Everest is the highest point on Earth. We also have an absolute minimum, which would be the bottom of the Marianas Trench under the Pacific Ocean. That's the lowest point on Earth that we know of at this time. Now, an absolute in this sense means either all other y values are below that for the absolute maximum, or all other y values are above that for the absolute minimum. There are also things that we can call relative extrema. For a relative extrema, this means that the value is not the absolute maximum or minimum, but it is higher than the ones around it. So, for example, the mountains in Colorado are all relative extrema. They are higher than the land surrounding them, but they are not the highest point on Earth. We can talk about the relative maximum for the United States, which I believe is Mount McKinley in Alaska. And we can also talk about the relative minimum in the United States, which is Death Valley out in California. But we can also talk about local relative maximums and relative minimums. And for that, we need to define some interval, and over that interval, that is the lowest y value for a minimum or the highest y value for a maximum. Relative means relative to all the points nearby. Absolute means to all points on the graph altogether. So let's take a look at the theorem that you can see in front of you. This theorem is basically making a mathematical statement of what it means to be the absolute maximum at the point x equals c over some interval I. That means that the y value at c, f of c, is higher than or equal to all other y values over the interval. Now, let's go on and take a look at another theorem. Our next theorem is called the extreme value theorem, and this is the one that we talked about in class yesterday. For this theorem, it gives the conditions over which a function or its graph is guaranteed to have an absolute maximum over an interval and an absolute minimum over the same interval. So the conditions in order to be guaranteed that there's an absolute maximum and an absolute minimum are basically twofold. One, it has to be a continuous function. That means that over that interval, you have to be able to draw the graph without picking up the pencil. It also means that the interval has to be closed and bounded. Closed means you must include the endpoints. You can't leave one of the endpoints open, like at a hole or a vertical asymptote. They have to be closed using square brackets. Bounded means that you cannot go to infinity or negative infinity on the right or the left, respectively. It is true that technically negative infinity to infinity is considered both an open interval and a closed interval, and that's why we need to add the word bounded. Now, let's take a look at some pictures and find out why the extreme value theorem is important and why it is not guaranteed that a graph will have an absolute maximum or an absolute minimum over an interval if we fail to meet one of these conditions. This is out of your textbook. This is figure 4.13. Here are the first three graphs out of that figure. If you're looking at graph A on the left, this is the graph of x cubed. It is definitely continuous over its entire domain from negative infinity to infinity. However, that domain is not bounded. Negative infinity and infinity are not finite real numbers, and in that sense, they have no bound. Because of that, there is no absolute maximum and no absolute minimum over the interval negative infinity to infinity. I can't say what the highest y value is because there is no highest y value. Likewise, there's no lowest. On picture B in the center, this is the graph of f of x equal to 1 divided by x squared plus 1, the quantity. Again, this is over the entire domain of that function, negative infinity to infinity. Notice that this is also not a bounded interval. Just because it is not guaranteed by the extreme value theorem doesn't mean it doesn't occur. This particular picture definitely does have an absolute maximum of y value 1 occurring at x equals 0, but it does not have an absolute minimum because the graph approaches the x-axis nearing 0 on both the far left and the far right as x goes to negative infinity and positive infinity. Again, it's the lack of the bound on the interval that creates the possibility to not be guaranteed to have absolute extrema. Let's look at the last one in part C. This is the graph of cosine of x, also from negative infinity to infinity. In this case, even though the interval is not bounded, negative infinity to infinity, we have both an absolute maximum and an absolute minimum. Remember that the absolute extrema is the y value, the x value is where it occurs. In this case, the absolute maximum for cosine, and for sine as well, is the number 1. It occurs infinitely often. For cosine, the value of 1 occurs at the even multiples of 2 pi. The absolute minimum is negative 1, and it occurs at the odd multiples of pi. If we look at the next 3 graphs, also coming out of figure 4.13, we see 3 more cases. In all 3 of these cases, the interval is closed and bounded. By closed, we mean that it is closed on the far left and includes the far left endpoint, and closed on the right, including the far right endpoint, with the exception of the third figure in figure F. Let's look at F first. It is closed on the left side because it is 0 next to a square bracket. The right side, however, is open because we have a round parentheses near 2. This means that as x approaches 2 from the left side, it could go off to infinity. This fails to prove that there has to be an absolute maximum, and in fact, in this graph, there is not. There is an absolute minimum, but because the region is not closed and bounded on both ends, it's not guaranteed. Now let's look at the first 2 graphs. The first 2 graphs are over closed bounded intervals. Both endpoints are values, and they are not including, sorry, I'm getting an email. We'll just ignore that for a moment. They are including the endpoints, and they do not include infinity or negative infinity. Because they're closed and bounded, not infinity or negative infinity, we are guaranteed that extrema will exist provided the function is continuous over that closed bounded interval. The picture in graph D is not continuous. There is a jump in the graph at x equal 2. Because of that, we are not guaranteed to have either an absolute maximum or an absolute minimum over that interval. In fact, we do have an absolute maximum of y value equal to 2 occurring at x equals 0, but we are not guaranteed. There is no absolute minimum because while it is true that it looks like it is approaching the y value of negative 2 as x approaches 2 from the left, it never gets there. There is no lowest y value. You can't say it's negative 2 because at negative 2 there is a hole. This means that there is no minimum over that closed bounded interval. And again, this is due to the lack of continuity. Graph E is the only one that meets all the conditions. It is a closed interval from closed 1 to closed 4. It is bounded because neither 1 nor 4 are infinity or negative infinity, and that graph can be drawn without picking up the pencil, meaning that it's continuous. Thus, there must be some y value that is bigger than all other y values, or the same value, and some y value that is lower than all the others, or the same y value. Saying that it occurs does not mean it has to occur only once. It could occur many, many times, but there is one unique y value that is larger than all the others, and one unique y value that is lower than all the others, though they can occur many different times. Let's move on to the next piece. In the next definition, we want to define mathematically what it means to be a local maximum or local minimum. This would be like our mountains in Colorado or the bottoms of our valleys. While they are the highest or lowest points nearby, they are not the highest and lowest on Earth, so they are not the absolute maxima or the absolute minima. What it means to be a local maximum or a local minimum means that there is an open interval about that location, x equals c, where the y value at c is either greater than or equal to all other y values within that interval, or it is lower than all other y values within that interval for a minimum. Now let's take a look at the picture and see what we're talking about. In this picture, you can see that we have both what looks like the top of a hill at x equals 0, the bottom of a valley at x equal 1, and a cusp or corner up at x equal 2. It is clear that the y value at x equals 0 is taller than the ones immediately to its left and right, so it is a local maximum. However, it's not the absolute maximum because the y value when x is 2 is higher. So the y value at x is 2 is the absolute maximum, and the y value at x equals 0 is a local maximum. Similarly, the y value at x equal 1 is a local minimum because while it is lower than the ones immediately to its left and to its right, it's not the lowest ones on the graph. The ends on the far left and the far right appear to extend towards negative infinity forever, which means there is no absolute minimum on this graph, though we do have a local minimum. This graph is also suggestive of where we will find our local minima and our local maxima. They will occur at the tops of hills and bottoms of valleys and at corners and cusps. In other words, at the places where the slope of the tangent line is 0 or where the first derivative does not exist. We have a name for such points. They're called the critical points of the graph. Let's put that definition on here now. We now have the definition of what a critical point is on the graph. Provided that C is an interior point in the domain of F, meaning it's not at the endpoint of a closed interval, then C will be a critical point of the function if the derivative is 0 there or if the derivative is undefined. This will include the tops of our hills, the bottoms of our valleys, our corners, and our cusps. However, it does include more than that. It is also possible to have a graph like the cubic function that has a critical value that's neither the top of a hill, nor the bottom of a valley, nor a corner, nor a cusp, and yet the derivative is 0. Here is the graph of x cubed. Remember that there is that one spot right there in the center where the tangent line appears to go horizontal. At that point, right there in the center, the tangent line goes horizontal, which means that the derivative there at 0 is 0. However, that is not a relative extrema. It's neither higher than all the points to both left and right, nor lower than all the points to the left and right. Being a critical point does not guarantee that you are an extrema value. It just opens the door and makes it possible. There is another theorem called Fermat's theorem, but this is not something you need to know by name, but you do need to understand it. The idea is this. Suppose I do have a local extrema. That means that I either have a local maximum or a local minimum at C. And suppose that the derivative does exist there. If the derivative exists, it cannot be a corner or a cusp. If the derivative exists and it's a local max or a local min, then it must be a hilltop or a valley bottom. In that case, I can say for sure that the derivative at that point must be 0. That does not mean that just because the derivative is 0, that it has to be a local extrema. Again, refer to the graph of f of x equal to x cubed for a counterexample. How will we find the location of absolute extrema on the graph? To be guaranteed that the absolute extrema exist, remember that the function must be continuous, drawn without picking up the pencil, and that the interval must be closed on both ends and bounded, not going to infinity or negative infinity. If that is the case, then we are guaranteed that there is an absolute maximum y value over the interval and an absolute minimum y value over the interval. The only places that these extrema can occur are at hilltops, valley bottoms, corners, cusps, or at the endpoints of the closed interval themselves. Here's a strategy for finding these places. First, if you're given the closed interval from a to b, evaluate the function at x equal a and x equal b. Then take the derivative of the function to find the critical points of the function where the derivative is equal to 0. Then consider the critical points where the derivative is not defined. It is possible that neither of these cases exist. Once you've located the critical points, plug those values into the function and find their y values. Compare all the y values you found in steps 1 and 2. The largest y value is the value of the absolute extrema. Where it occurs is the x values. The absolute minimum is the lowest y value you found in steps 1 and 2. Where it occurs are the x values. Let's move on and take a look at a couple of examples. Looking at the function, we need to think about where this function might have absolute extrema. First, does it meet the conditions of the absolute extremum theorem? And the answer is yes. This is a cubic function, which is a polynomial, so it is continuous and defined on all real numbers. That means it is definitely continuous on the closed and bounded interval from -1 to 3. Now I'm going to plug in the value -1 into the function to find the y value when x equals -1. When I do that, I come up with the following value. This will give me -1/8 plus 1/2, which is the same as -1/8 plus 4/8, which gives me 3/8. Now I'm going to plug in 3 into the same function to see what the y value is at the far right endpoint. This is going to give me 1/8 times 3 cubed minus 1/2 times 3, which is 1/8 times 27 minus 3/2. Rewriting 3/2, I can express this as 27 over 8 minus 12 over 8, multiplying the 3/2 by 4 over 4. This would give me 25/8, I believe. Of the two y values I have so far, 25/8 is bigger than 1. In fact, it's bigger than 3, so it is definitely the maximum so far. That does not make it the absolute maximum. I need to check the critical points if there are any. To find the critical points, I need to take my function and find the derivative. To find the derivative, you will apply the rules you've learned so far this semester. This is 3/8 x squared minus 1/2. When would this be equal to 0, or when would it be undefined? Consider the two cases separately. 1. When is f prime equal to 0? Well, I will take this expression and set it equal to 0 and solve. To get rid of the fractions, the easiest thing to do is to multiply both sides of the equation by the common denominator, 8. This gives me 3x squared minus 4 equals 0. By moving the 4 to the other side and then dividing by 3, I can get the equation x squared equals 4/3. Taking the square root of both sides, I get x could be plus or minus the square root of 4/3, which will reduce to plus or minus 2 divided by the square root of 3. Now I need to think about my interval. Are both of these values within the interval given, which is -1 to 3? For this, you may want to have a calculator handy. If you take your calculator and you plug in 2 divided by the square root of 3, you should come up with the value of 1.1547 ... That means that since this value is roughly 1.15, the negative value is not inside of my interval, which only begins at -1 and goes to 3. The negative 1.15 is out of the interval, so I don't consider it for where the absolute extrema could occur. I can look at 2 divided by the square root of 3, so I will consider that value and plug in that value into the original function to find out what the y value is there. The original function again was 1/8 x cubed minus 1/2 x. So I have 1/8 times that value cubed minus 1/2 times 2 over the square root of 3. In order to simplify this, you'll have to apply some of your algebra. Pause the video and simplify it, and then see if your answer matches mine. When I reduced and applied arithmetic, I got -2 divided by 3 square roots of 3, which is roughly -0.385. This is a possibility for an absolute extrema over the closed interval from -1 up to 4. Now I need to consider my second case. My second case for where the critical points occur is when the first derivative does not exist. In this case, however, recall that our first derivative is here in the square box out of red. 3/8 x squared minus 1/2. There is no x in the denominator and no even radical. That derivative exists for all real values, which means that there are no critical points coming from the first derivative not existing. They exist everywhere. What is the final result of all of this work? The final result is that I have found an absolute maximum, and the absolute maximum is the y value 25/8, and it occurs at x equals 3, which was one of the endpoints. The absolute minimum over this interval is occurring at the critical point we found from the derivative equal to 0. So our absolute minimum of, in this case, I would use the exact value, -2 divided by 3 square roots of 3, and this occurs at the x value 2 divided by the square root of 3. This is how you find the absolute extrema over a closed and bounded interval. This concludes this video over section 4.3.